Alright, when taking a look at radicals, there's a couple things we need to take a look at before we can actually get in. So, I need to familiarize you guys with something called radical notation. And what this means is, this just explains the way that radicals are actually presented and what you're going to be seeing. So, this entire symbol here is going to be called a radical sign. A radical sign. This entire thing is called a radical sign. Whatever's inside of our radical sign is going to be called the radicand. So whatever's inside is the radicand. Whatever number's in front of our radical sign, so in this case, let's say it's a 2, this is going to be our coefficient. Finally, the last thing we need to take a look at is whatever number is on this point or at the tip of this little pyramid here, and this is called the index. So let's say it's a 3. A 3 means we're going to be using the cubed root. So if it was a cubed root, what that basically means is we're taking the cubed root. That means we're finding a number which, when multiplied by itself 3 times, since we have this 3, a cube, equals another number. So the output of this. So let's see what this actually means. So if there were nothing actually in front of our index, or nothing there for our index, again, we're assuming it's a 2. So there's an invisible 2 here that we use as our square root. For a 4, we're going to find 4 numbers. So again, it depends on what your index is. And this is important when we're taking a look at adding and multiplying radicals, because we have to have 2 things in common. We have to have the radicand alike, and we have to have our index alike. And if our both criteria are met for that, then we can actually begin to add. And it's essential that we're actually taking a look at, again, the radicand and the index before we actually proceed with these processes. So now let's learn how to simplify radicals. Let's learn how to simplify them. So how do we simplify this expression here? So the way we actually begin to simplify this is, again, in our radicand, what we need to do is we need to break everything down. This symbol here, or this index, is going to be an invisible 2. Remember, we have an invisible 2 there. And we're just looking for groups of 2, essentially. So if we were to break down the 75, it'll turn into 25 times 3 times 5 times 5. In terms of this x, this breaks down into x times x times x times x times x times x times x. And this is just for visual representation. And this y is going to break down into y times itself 4 times. So now that we've actually broken down everything, we can rewrite that in our square root symbol. So our square root symbol, let me just bring everything down here. So everything is rewritten in our square root symbol. Remember that we're looking for groups of 2 here. So, because our index is going to be 2. If we're looking for groups of 2, we're looking for pairs, or order pairs. So, do we have a group of 5? Yes, we do. We have 2 5s being multiplied by each other. So, that is one group of 2, which we're going to move out. In terms of this x, how many groups of x's are we moving out? 1, 2, 3. So, we're going to move an x out, an x out, an x out. And we're moving 3 x's out. So, we have 5 times x times x times x being moved out. In terms of our y, we have 2 groups of y, which we can move out. So we're going to move out these 2 groups of y. So what's going to be our coefficient now is going to be 5 times x times x times x times y times y. And what's left inside our square root symbol is going to be an x and a 3. And that's going to be what's remaining. Now we can actually simplify our coefficient. So 5 times x is 5x. 5x times x is going to be 5x squared. 5x times y is 5x squared times, or 5x squared y. 5x squared y times y gives us 5x squared y squared. So now that we've actually broken down and moved everything out of our radical sign, we can actually begin to simplify. This turns into x cubed, so 5x cubed. And this turns into y squared. What's left inside is going to be 3x. And it's crucial that we actually do this, because when we're taking a look at restrictions, right? If we were to ask to find the restriction on this specific given expression, notice how the only thing left in our radical symbol is an x. The only thing left in there is an x. So if we only have an x left there, that tells us something, right? Our y doesn't have any restrictions. So it's good we simplify before we actually do this. And the other reason being is you're going to notice that y is being raised to an even power. So when numbers are raised to an even power, if they're negative, it doesn't matter. Because let's say we have negative 2 to the power of 4. What that gives us is 2 times 2 times 2 times 2. That gives us 16, even though it was negative. If it's an odd number, however, that's where we start having restrictions, right? So if we have negative 2 raised to the power of 3, an odd number in this case, negative 2 times negative 2 times negative 2. That gives us 4 times negative 2 equals negative 8. And we don't want negative numbers in our radical sign, because remember, we're taking the square root in this case. So if we take the square root of a negative number, that'll give us an error. So you're probably wondering, what is the restriction? So how do we do the restriction on this? What we're doing is, it's the same thing as our NPV essentially. But instead of setting it equal to 0, we're setting it greater than or equal to 0. Because in this case, our radical or our variable can be greater than or equal to 0. And since we simplified this, the only variable in our equation or in our radical sign that actually needs to be set and have a restriction on is going to be 3x. So 3x is greater than or equal to 0. Solve for x. X is greater than or equal to 0. So x has to be a positive number. You're probably wondering, why is it or equal to 0? Because if we're taking, if the number is 0, if it's equal to 0, 3 times 0 gives us 0. The square root of 0 still works. It doesn't give us an error. So that's why we can actually equal 0. So now let's actually find the restriction on this expression. So what 24 breaks down is into 12 and 2, 4 and 3, and 2 times 2. So we get 2 times 2 times 2 times 3 as our broken down and simplified version of 24. In terms of a, that breaks down into a squared times a squared, because I'm not going to write all those a's, but this represents a 2 group of a. In terms of this can break down, this b can break down into a b squared times a b, because I don't want to write all those letters out. So now, if we have a square root, we're looking for groups of 2. So we want to remove groups of 2. So this pair of 2 here is going to be moved out. So that's going to be our coefficient. What's left is 2 times 3, which is 6. A squared is a group of 2, so we're removing a. A squared is another group of 2, which we're removing a. So we have 2 a's being removed and turned into our coefficient. And we have 1b squared, so 1b being turned into our coefficient. What's left in our root sign is going to be 6b. So a times a is a squared, so we get 2a squared times b root 6b. 6b. So now that we've simplified this, we can actually find the restriction. So we're setting whatever our radicand is greater than or equal to 0. So now let's set 6b greater than or equal to 0. Divide by 6, and you get b is greater than or equal to 0. And that is the only restriction, because again, we're following that rule, because b is an odd exponent, meaning that when we raise it to an odd exponent, we're still going to get negative numbers. So we have to be greater than or equal to 0. But in terms of our a, it's an even exponent. The negative signs will cancel out. So again, that is what we're doing when we're finding restrictions. All right, now, adding and simplifying radicals. How do we add and simplify radicals? This is where this terminology is going to be key. Because again, we need to understand what's actually going on in terms of our terminology. So here, what we have is 5 root 8 plus root 98 minus 2 root 18. Since we don't have any like terms, so our radicands aren't the same, we can't actually add. And remember when I mentioned earlier, our indexes have to be the same and they're all square roots, so it only falls under one criteria. However, if we break it down and they all simplify to have the similar radicand, that is when we can begin to add. So let's simplify each individual expression to begin with. Alright, so let's simplify this 5 root 8. So what happens here is 5 root, and what happens in this 8 is going to simplify to 2 times 2 times 2. 2 times 2 is 4, 4 times 2 is 8. So we're taking out a group of 2, and we're multiplying it by our coefficient here. So we have 5, and what's left inside is a root 2. This turns into 10 root 2. Now this root 98 is going to be a bit of a more pesky one, but what this can be broken down into is going to be, this can be broken down into 49 times 2 and 7 times 7. So if we rewrite that in our root here, we have root of 7 times 7 times 2. We remove this pair of 7 out, and we get 7 root 2 left inside. Now, let's simplify this last part. So we're going to be subtracting it, so make sure we're doing that. So 18, what does that simplify to? 9 times 2 and 3 times 3. So if we wrote that in our root sign, we have 3 times 3 times 2. And we have a negative 2 out front. So let's remove this group of 2. This one group of 3's out, or one pair of 3's out, and turn it into our coefficient. So when we do that, we get 3 times negative 2, and what's left inside is root 2. So that turns into 6 root 2, or negative 6 root 2. It's negative 6 root 2. And since we got rid of this negative sign already, this can be an adding. So now all we're doing is we're adding all these like terms. So 10 plus, all we're doing is we're going to add our coefficients, since we all have the same radicand being 2 and same index being 2 as well. So our index and our radicands are the same, meaning now we can actually begin to proceed to add. So 10 plus 7, since we're only going to add our coefficients, so now what we do is we only add the coefficients. We're not adding these radicals or these radicands up. We're adding what's in front of them. So 10 plus 7 minus 6. So 10 plus 7 is 17. 17 minus 6 gives us 11. And what's left is root 2. And that is how you add radicals. So now we have to multiply and fully simplify the following. So how do we do this? So what we're going to do is we're going to recognize this. So what's going on here is we have two individual things going on. So effectively what we're doing is when we're multiplying one-term radicals, because this is just one term, and what a two-term radical would look like this. It would be something like this. It doesn't have to be exactly, but that is like a bi-term radical. When we're adding single-term radicals, or multiplying single-term radicals in this case, what we're doing is we're multiplying our coefficient by our coefficient. So we have negative 10 times 2, which gives us negative 20. And we're multiplying our radicand by our radicand. So 5 times, or root 5 times 50. And that gives us root 250. Because 5 times 50 is 250. So now all we have to do is we have to simplify. How do we simplify? This root 250 is a big number. It's not fully simplified. We can still break it down. So let's take a look at that. 250 can be broken down into 25 times 10, 5 times 5, and 5 times 2, all under this root symbol. Remember, we have a negative 20y out front. We're looking for a pair of 2, and we have this one pair of 5, which you can move out front. So we have negative 20 y times 5 root whatever is left inside, so 5 times 2 is 10. all we have to do is further simplify our coefficient, and we get negative 100y root 10 as our final and simplified answer. That is how you multiply single radical expressions. Alright, now when we're taking a look at something like this would be a two-term radical, opposed to our last one, which was like 2y root 3. Because we actually have two radical symbols, or two things that we're actually doing. So this is split by a subtraction sign here in this case, so there's going to be a different process. If we're squaring this, we need to treat this like it's a polynomial. We need to treat it like it's a polynomial, or in this case, a binomial. We need to treat it like a binomial. If we're squaring it, we need to treat it like it's a binomial. In order to do that, you have to follow our FOIL principle. So remember that when we're squaring something, we're multiplying it by itself. And honestly, that is a better definition. And in this case, this unit, I like to use that definition better. To multiply by itself is better than just squaring each individual term, because that will get you a wrong answer no matter what. But if you multiply something by itself, no matter what you do in this unit, it'll be right. So let's take a look at what we actually have to do when we have this. So you're probably going to recognize this. This looks something like a binomial foiling, right? And that's exactly what we're going to do. We're going to FOIL. So we have this first and inner. And remember, when we're multiplying these radicals, we're multiplying our coefficient by coefficient and radicand times our radicand. So let's try this. 2 times 2 is 4. What does our radicands multiply to? So we have the square root of 5 times the square root of 5. The square root of 5 times the square root of 5 equals 5. These square root signs cancel out. So we get 5. Now, we have 2 root 5 times negative 3 root 2. Negative 3 times 2 gives us negative 6. We're going to multiply our radicand by radicand now. So we have root 5 times root 2 gives us root 10. Now, moving on to a different one. We have this here. Negative 3 times 2, or negative 3 times 2 gives us negative 6. Root 2 times root 5 gives us root 10. Finally, we have this last one here. Negative 3 times negative 3 gives us 9. And 2, our root 2 times our root 2 times root 2 gives us 2. These root signs will cancel out. So you get 9 times 2. So now, let's take a look and try to break down and simplify further. So we have this over here. So 4 times 5 is 20. And then we have this part over here, which 9 times 2 is 18. So we have 20 plus 18. And we have negative 6 root 10 minus 6 root 10. And since these expressions, these radicals both have an index of 2 and the same radicand, we can add the coefficients. So negative 6 plus negative 6 is negative 12 root 10. And then we have this on the end, which is going to be 18 plus 20, which is going to give us 38. And that is going to be your final answer, fully simplified. That is how you add, or this is how you multiply and FOIL radicals. So now when we're taking a look at fractions, typically when we're dealing with this radical unit or any unit beyond, it's technically improper to be dividing by a root sign. And what I mean by this is if we have an expression that looks like this, 2 over root 3, we're gonna need to do something to actually get rid of that root sign, because we don't want to have a root sign on the denominator. And there's a couple reasons why, because we actually, and in order to do this, to simplify and rationalize this process is going to be, and in order to do so, this process is going to be called rationalizing. So when we're multiplying and fixing this radical sign on the bottom, we're going to rationalize. So order to do that, we need to multiply the denominator and the numerator by root 3. And we're multiplying both because if we just multiplied our numerator, then we would be completely changing our expression. We're keeping it equal by multiplying both sides. So 2 root 3. And then we have root 3 times root 3 on the bottom, which gives us 3. And that would be your fully simplified, rationalized version. And notice how we're not dividing by a radical sign here. We actually have this expression which has no root sign on the bottom. And you're going to notice that these are actually equivalent. When you put 2 root 3 versus 2 root 3, or 2 over root 3, compared to 2 times root 3 over 3, it actually gives you the same thing, the same number. So we're just rationalizing it to make it more proper. Where a different process arises is when we take a look at, again, these two-term radicals. So we're dividing by two-term radicals, and what we're going to do here is we're going to have to deal with something. It's called a conjugate. A conjugate. Well, what is a conjugate? So we have to deal with this thing called the conjugate. The conjugate is going to be the opposite of what we're actually dividing by. So we're taking the opposite number. So we have 15 minus 2 root 3. The conjugate, since it's the opposite, would be root 15 plus 2 root 3. So that is the conjugate. That's all the conjugate is. And taking the conjugate is actually, we're doing the same thing. We have the same goal here. We're trying to rationalize this expression. So we have to take the opposite when we have a two-term radical. So whatever we do to the top, we're going to do to the bottom. So we have root 15 plus root 2 root 3. And this is, again, going to be a process of FOILing, at least on the bottom. Since we have one term being multiplied by 2 in the numerator, we can actually use our distribute property. So 5 times this invisible 1 gives us 5. Root 3 times this root 15 gives us root 45. Now, we have this root 5 times this root 2, or 2 root 3. So 5 times 2 gives us 10. Root 3 times root 3 gives us just 3. Now, in terms of this denominator, it's going to be a little bit more of a complicated process. Because again, we're going to have to FOIL it, and we don't like FOILing. Because it's a lot of work, but it's okay. So, now that we've written out our numerator, we can actually do our denominator now. So let's begin to FOIL. So, we have this first term being multiplied by the first. Root 15 times root 15. You're multiplying it by itself, so those signs are going to cancel out. Root 15 times 2 root 3. Remember, we're just going to, since there's an invisible 1 here, we're multiplying this invisible 1 by this 2. We get 2 root 15 times 3 gives us root 45. Now we're going to multiply this negative here. So we have minus 2 and 3 times the root. So we're multiplying our radicands here. So our coefficient by coefficient. And you have to pretend there's an invisible 1 whenever you can't see your coefficient. Remember this. So negative 2 times 1 is negative 2. Whatever's inside our radicand, which in this case is going to be 3 times 15, is going to be root 45. Now we have our final FOIL, which is going to be negative 2 times 2, which is negative 4. And on our last one, we have root 3 times root 3, which is going to be 3. So you're going to notice that we're going to have 2 root 45 minus 2 root 45. You're adding it and then you're subtracting it. Does that mean they cancel out? Yes, it does. So what you're left with is 15 minus 4 times 3 on your denominator. 4 times 3 is 12. 15 minus 12 is 3. So this whole thing divided by 3. So you have 10 times 3 is 30. And now, what we have here is this. Except this is not fully simplified yet. Because 45, it can be broken down still. 45, so let's break down this 45. 45 can be broken down into 3 times 3 times 5. 3 times 5 is 15. 15 times 3 is 45. We're bringing out this group here, and we get 5 times 3. That gives us 15, and whatever is left inside our root is root 5. Plus 30 over 3. What's common? What's a common factor here between all three of these terms within our expression? 15 divided by 3, or our common term is going to be 3. So let's divide everything by 3. So 15 divided by 3 is 5, root 5. 30 divided by 3 is 10. And root 3, or over our denominator, 3 divided by 3 is 1. When we divide by 1, we don't need to write out. So this is going to be your fully simplified and final answer. And that is how you rationalize and use your conjugate. So here we have another fractional expression, and we're going to want to rationalize it because we don't want to be dividing by these ugly roots on the bottom. This is a 3, by the way. So what we can do is we can use our applied knowledge. What is our conjugate? Root 5 minus root 3, because we're just flipping the sign here, and that's our conjugate. Multiply both sides, or both the numerator and the denominator. And again, what we're doing here is since we have to identify what process we're going to be using. Since there's two terms being multiplied by two terms, we're using FOIL. In our last one, we had one term in our numerator being multiplied by 2, which is why you use distribute property. But in this case, we have two terms being multiplied by each other. So it's going to look like this. Now we're going to have this process of foiling. So 3 times this invisible 1 is going to give us 3. And root 5 times root 5 gives us 5. So we have 15 in our numerator so far. Now what we can do is multiply this by this. So pretend there's a negative 1 there. So 3 times negative 1 is going to be negative 3. We're going to multiply our radicand by our radicand. So root 5 times root 3 gives us root 15. Now we have this. We have an invisible 1 here, and we're pretending there's a 1, because remember, when there's no coefficient there, it's an invisible 1. So we have 1 times 1 is just 1, so we don't have to write that. And we have this root 2 being multiplied by root 5. That gives us root 10. Now, we have this final process. Root 2 times root 3, or negative root 3. So we're going to have a negative sign, since it's negative, and 2 times 3 gives us root 6. Root 6. Now, our denominator, we're going to have to rationalize or FOIL out our denominator here. So let's FOIL this. I'm gonna move this aside. So let's FOIL this here. So this first part, root 5 times root 5 gives us 5. Root 5 times root negative 3, because remember there's negative 1, or there's 1s in front of here because they're invisible. 1 times 1 is negative 1, so we're going to have negative 1, or if you don't want to write it, it's okay. And we're multiplying our radicand by our radicand, so we get root 5 times root 3 gives us root 15. Now, what we can actually do is do this part. We're foiling. Root 3 times root 5 gives us plus root 15. Because this is positive. Now we have root 3 times root 3, and pretend there's invisible 1s here again. We have 1 times negative 1 gives us negative. And then we have our radicand being multiplied by our radicand, giving us root 3 times root 3. Those root signs cancel out, and they give us 3. So again, you're going to notice something here, that these actually cancel out. You have negative root 15 plus root 15. These are gone. And what you're left with is 5 minus 3 in your denominator. 5 minus 3 simplifies down to 2. So, after all of that, all of that, we can begin to look for a greatest common factor or try to add. So let's try to break down our roots. Can 15 be broken down any further? You have 5 times 3. No. Can 10 be broken down any further? You have 5 times 2. No. Can 6 be broken down any further? You have 3 times 2. No. So these are all fully simplified, although it doesn't look like it. Like it looks like a bit of a mess here because we have this negative root 6 plus this root 10 here, which is like, it just looks horrible, right? It doesn't look simplified, but it actually is. But all we're looking for here is we're looking for if there's a greatest common factor that we can divide everything by and simplify. But since there's ones, we can't do anything with this. This is fully simplified. This is going to be your final answer. This is how you rationalize. Notice how there's no radical signs within our denominator because we've divided or we've multiplied by our conjugates to get rid of them. And that is how you actually rationalize. That's the whole goal of using the conjugate, is to make sure we're not dividing by root signs. All right, question number 1. Which of the following statements are true? So it's going to be like a multiple, I'm assuming. So let's take a look at this first one. We're comparing an input of x to an output of what we're doing with x squared. So if we take a number, we're saying the range of where x is greater than 0. So we have to have a positive number. If we're taking a positive number and we're plugging it in, so let's say we have 1, which is positive, and we take the square root of 1 squared. Does that give us 1? Yes, it does. This statement is true. Now taking a look at statement 2. We're comparing this input versus the output. So let's try any number that's less than 0. So x is less than 0. So any number that's less than 0 is going to be, a number that's less than 0 is going to be negative 1. So let's try negative 1. So negative 1 equals square root of negative 1 squared, which gives us 1. This gives us 1. 1 equals 1. This is true. So far 1 and 2 are true. Now let's take a look at this. X equals x squared for any number where x is an element of the real. So any number. So I'm going to try a negative and a positive number here. So let's try negative 1. So let's plug in negative 1. Does that equal the square root of negative 1 squared? So negative 1 squared gives us 1. Square root of 1 is 1. Negative 1 does not equal 1. So that means this actually is wrong. Because when we plug in negative numbers, it doesn't give us the same input as it does as output. So this is going to be wrong. So this is not going to be a true statement. Now let's check our last one. X equals cubed root of x cubed for where x is an element of the reals. So if we're taking the cubed root of x cubed, these actually cancel out. That leaves us with any number that we can plug in. So x equals x. So this would be true. Any number that we're plugging in is what we're going to get out. And this is also true because remember, when we're raising something to an even exponent, even if it were a negative, we're still going to get a negative output. So like for example, if we were to put in negative 3 cubed turns into negative 27. Because again, it's not canceling each other out, as opposed to an even root, or opposed to an even exponent. So the answer to this question here is going to be 2, 1, 2, and 4, which is going to be B. So now we're looking at which of the following is the. So now we're going to do this problem here. So the square CDEF has this area of 40 square units. So CDEF, this whole area here is going to be 40 units. And remember that our area is equal to, in a square at least, is equal to side length times side length. So 40 equals our side length times side length, or side length squared. So how do we do this? Let's solve for s. Let's take the square root, and we're going to get square root of 40 is equal to each individual side length. So now that we've actually found our side length, what we can do is we have to look for the length of segment AF. So we're looking for from here to right here. So the way we can actually do this is if we calculate this whole length, and subtract root 40 from it, because that'll give us this isolated length right here. So we're looking for the hypotenuse of this triangle. So let's find it. So we have a squared plus b squared equals c squared is our Pythagorean theorem. We're going to plug in our value. So 5 squared plus 15 squared equals c squared. And let's do this in my calculator here. 5 squared plus 15 squared gives us 250 equals c squared. And now we're going to square root this because we're going to find c on its own. So c is going to be square root of 250. So if this whole length here from A to C is going to be 250, 250 minus our length of root 40 will give us just this isolated length of A to F. So now let's do this. So this entire length, this C, represents the length of the hypotenuse. If we're subtracting the length of the square from it, that'll give us the length of A to F. So let's do this. So if root of 250 minus the root of 40. Remember, in order to subtract, we need to do a couple things first. We need to break this down. So you have 25 times 10. 5 times 5 and 5 times 2. This gives us 5 root 10 minus our 40, which can be broken down into 2 times 20 and 4 times 5 times 2 times 2. So we have 2 times 2 times 2 times 5 within our root sign. We're bringing this out front and get 2 root 10. And notice how these are the same. They have the same radicand, meaning we can actually subtract. So, and they also have the same index of 2. So we can actually subtract. So 5 minus 2 is 3 root 10. Our final length here is going to be 3 root 10 meters. And that's going to be your final answer of the length from A to F. So, looking at question 7, we have a equation which models the swing of a pendulum where L is the length in meters and T is the seconds. If we're looking for the length and we have the time, we just have to plug in our value. So we have the value of 9 seconds. So we're going to plug in 9 equals 2 pi root of our length times 9.8. Alright, length over 9.8. So now all it's a process is of isolating for L. So the way we isolate for L here is we're going to divide both sides by 2 pi. So 9 divided by 2 pi. So to cancel out this 2 pi over here gives us the square root of L over 9.8. So now we actually have to square both sides. So let's square both sides. And you get 9 squared, which is going to be, or you can just leave it like this for now. 9 squared over 2 pi squared equals L over 9.8. Now what we can do is we can multiply both sides by 9.8. And you're going to get 9.8 times 9 squared over 2 pi equals our length. So now that we've actually isolated our variable, we can actually put this in our calculator. So 9 times 81 over 2 pi. That gives us our length, or at least our length. So we're asked to round this to the nearest centimeter. So that gives us our length as 126.33 centimeters. However, we're asked to round to the nearest meter, nearest centimeter, so we get 126 centimeters as our length of the full swing. If our pendulum took 9 seconds to complete, that is the length, 126 centimeters. Alrighty, finally, we're going to explore something called radical equations. So we've done adding, multiplying, and dividing. what we need to do now is actually take a look at how to do radical equations. So, in order to start this, what I like to do is isolate our radical sign. So, in order to do that, we need to add 7 to both sides, add 7 to both sides, and you get root 3x plus 4 equals 8, and now we're going to both divide both sides by 2. We're going to get root 3x plus 4 equals 4. Now, what we can do is in order to get rid of our square root sign, we need to square both sides. So we're going to square both sides. That gives us 3x plus 4 equals 16. From here, we need to subtract 4 from both sides, and we get 3x is equal to 12. So 16 minus 4 equals 12. And we solve for our x. So now we can divide both sides by 3, and we get x is equal to 4. So now we need to actually check if our solution actually works and if it's extraneous or not. So the way we do this is we plug it back into our original equation. So we have 2 times the square root of 3 times 2, which gives us 6, plus 4, minus 7 equals 1. If this is true, then our answer is going to be correct. So now we need to actually check if our solution is correct. So we have 2, and so now we need to actually check if our root is extraneous or not, meaning if it actually works in our equation. So we need to put 2 square root 3 times 4 as our x, because we got x is equal to 4, plus 4 minus 7 is equal to 1. So we get 2 root 12 plus 4 minus 7 is equal to 1, and you get 2 times the root of 16 minus 7. You get 2 times 4 minus 7. You get 8 minus 7 equals 1. And 8 minus 7 is 1, and 1 is going to equal 1. So both sides, left side is going to equal right side, meaning we have no extraneous solutions in this case. So, hopefully this video helped. It's a very brief and quick video on just how to do the basics and fundamentals of radicals. If there is a need to go in depth or at any point, I mean, there's plenty of practice resources out there that you guys can take a look at and other videos for sure. But I hope this video, helped you understand the fundamentals of how we take a look and explore radicals. Sorry for it being a little late because it's been a busy week for me, at least. So I haven't been able to pump out these videos, but over the next 2 weeks, I think I will be getting a lot of stuff done and a lot of stuff out ahead of time. So just make sure we're looking forward to that. And if you enjoyed this video, just make sure to leave a like, and that'll be it for me.